All right, great. Well, hello and welcome back to Astronomy at Home, brought to you by the DiRAC Institute and Astronomy on Tap Seattle. We have a great talk coming up for you, but before we do that, just a little bit of business. We'll have a Q&A session after the talk with our speaker. Please feel free to add questions during the talk to the Zoom chat, or if you're following along on YouTube, to the YouTube chat. Then at about 9 p.m. after a short break after the Zoom Q&A, we'll be doing an Instagram live interview with the speaker on our AOT Seattle Instagram. I'll go ahead and put the handle in the Zoom chat for you if you'd like to join us there. All right, let's get to the good stuff. Our speaker tonight is a research scientist at both the University of Washington and the Vera Rubin Observatory. Please give a warm but mostly silent welcome to Dr. Meredith Rawls.
Thank you so much. Let me share my screen. All right, is that visible to everybody? I'm seeing thumbs up. Brilliant. Thank you very much for the welcome, Nicole. It's been really cool to help be part of this new little virtual Astronomy on Tap inspired DiRAC collaborated series. So this evening, I'm going to tell you a little bit about something that astronomers don't usually study or think too much about, and that is low Earth orbit satellites. So when we take pictures of the night sky, we usually expect to see things like stars and galaxies, but lately we've been seeing a whole bunch more satellites. So here's some examples of what I'm talking about. If I could select my window, we would really be in business. There we go. You may have known there was a comet that is visible, probably even tonight. I think it's its closest approach to Earth this evening. It was brightest a week or so ago, but you can still see it. If you have clear skies, you can go out literally when this whole talk is over, if it's dark enough, wherever you are. And you can look in the northwest sky and try to see Comet Neowise. A bunch of other folks had the same idea. And it turns out that when some of them went to take pictures, they saw a bunch of satellites as well, which was a little sad. They weren't expecting that. Depending on the artistic thing you're going for, one could say it detracts a bit from the beauty of the image. So this is what I want to talk about a little bit about tonight, is what is the impact that all of these new low Earth orbit satellites is going to have on astronomy and in a larger sense as well. So what are we even talking about here? So there already have been several hundred, maybe 1,000 low Earth orbit satellite already around Earth. This is not a totally new thing. What is new is that there's going to be tens of thousands of them in the next decade. And these are most visible near the beginning and the end of the night, so twilight-ish time, closer to sunrise and sunset. And they most drastically affect wide-field ground-based optical telescopes. The reason they're bright, of course, is from the sun. So these are not like, they don't have laser beams. They're not like shining a flashlight at us. It's all reflected sunlight. And it depends a lot on the exact shape and orientation and size and lots of different things of the actual satellite to figure out how bright it's going to be. It's actually a really complicated problem. But the brightness that we're seeing is reflected sunlight instead of all the stars and galaxies and other cool stuff we might be looking for. I also do want to step back for a minute. I'm going to be talking a lot about astronomy and science for the next little bit, because I'm an astronomer and scientist. And the first thing I think of is like, oh no, my pretty pictures. But there are kind of some bigger questions here I would like you to keep in the back of your mind as I go through some of the science. I don't think it's really easy to quantify what the stars in the sky are worth, and there's a very valid question of who decides. The sky doesn't belong to me, an astronomer. I don't think it belongs to satellite operators or any individual person or entity. We also can ask, what is the value of exploring the cosmos? This is something that we really want or need to do. And where nowadays can we actually go to find a naturally dark, star-studded sky? I wonder how many people watching this evening have actually seen the Milky Way. It's less common than it used to be to survey an audience. If we were all in the same place, I would ask you to raise your hand if you'd seen it. And I'm willing to bet that less than half of the people would raise their hands. It is a majestic sight, but it is something that we're slowly losing. There are also cultural significances to being able to actually see the night sky and use it for things like navigation. Many Polynesian cultures use wayfinding still, both in the past, but also still today as a traditional cultural practice. It also affects things like ecology. I didn't know this until recently, but apparently most migrating birds migrate at night, and many of them use the stars to do so. So if suddenly most of the stars are these moving satellites, that could have some pretty significant impacts. Again, not my area of specialty. You can look up more on that if you're interested, but there's just a lot of interesting things that I hadn't thought of as an astronomer who likes to look at pretty pictures of the sky and try to do science with them. So there you go. So, okay, so let's say we all agree this is at least somewhat of a problem. What can we do about it? So this image is actually from 2018, and it is before Starlink. So Starlink is SpaceX's thing. I'm saying it like you all know that, but it's pretty all over the news. I'm assuming you've heard of Starlink. There's 500 some odd Starlinks in orbit already right now. They just launched 60 like a week ago. And it's kind of the first big scale version of this that we're seeing. There's almost certainly going to be other companies that do the same thing because you can do all kinds of global network things if you have a bajillion satellites that are covering the globe. But in terms of astronomy and other wider dark sky related concerns, what we need is some combination of fewer satellites is like kind of the most obvious one. This isn't rocket science, right? If there's too many things in the sky, you could have fewer. That would be great. You can make them darker. There's a lot of interesting ways to do that I'll talk a little bit about. You could potentially make them smaller, though that is tricky because you need to be able to have like enough physical thing to do your mission. And then you can also make them predictable, which works to a point. And what I mean by predictable is that if I have a telescope and I'm trying to point at something, if I had software that told me, hey, maybe that thing's not actually visible right now, maybe come back in 5 minutes because there's like 5 satellites going over, that is helpful. But if you get to a point where there's tens of thousands of these things, like always, my little handy app that tells me when there's a satellite coming is probably going to just tell me I can never take a picture. So again, in combination, these are the broad swath options for mitigation. One thing that's important to note is that as astronomers, all of the different facilities that we have work together. So I work for Rubin Observatory. I do software development for processing all the images. It's going to come off this amazing telescope. It's under construction right now. The picture is on the right there is from Chile. And unfortunately, construction is shut down right now because everything is shut down right now, but it's there and it's fine. And we're going to finish it eventually. It's going to be great. But it's not the only facility. I'm going to talk a little bit about it because it's the thing I'm most familiar with. And it's actually also very affected by satellites. So those are 2 reasons you'll hear a lot about it tonight. But it's important to keep in mind that like if Rubin Observatory discovers something cool, that other telescopes are immediately going to need to follow up on that, either immediately or like within a week or a year or whatever, depending on what has been discovered. So you can't just pick any one telescope and say, okay, we're going to make things perfect for this one telescope and then you solved your problem. It's not that straightforward. I also want to briefly say happy birthday, Vera Rubin. Today would have been her birthday, which is very exciting. It's really cool that you should look her up if you don't know about her. Rubin Observatory is named after her and she was amazing. So, okay, a little bit more about low Earth orbit satellites. So as I said before, SpaceX is the first example, or Starlink is the first example of a mega constellation, and it's SpaceX's set of satellites. And we won't know until other companies do the same thing, but other companies should have similar satellite life cycles and sizes and altitudes, roughly speaking. So, but because Starlink exists, it's the thing we have to go off of. So right now they operate at a 550 kilometer orbit, and their goal is to provide broadband internet, which is a great goal. I'm not going to get into like the morality trade-off situation for like, internet or stars. It's not quite that straightforward. But there are some potentially questions about how affordable and accessible the internet that they or other satellite operators would actually offer that I would encourage folks to look into a little more. So satellites don't just appear in orbit, right? They got to get launched. Then when they're ejected from their spacecraft, they have to kind of get to their final orbit, which is called an orbit raise phase. So that phase takes an order of months, and they don't get to their final real operational altitude, which is called on station, for quite some time. And then that's the longest phase of their life. It lasts for something like 5 to 7 years before they are then deorbited and burned up in the atmosphere. Each of these phases, though, has different potential issues for brightness. So most of what I'm going to talk about tonight is the on-station phase, but the orbit raise phase is also a time when they can be really bright. That's what all those comet photos were, right? Those like lots of streaks together, really bright. That's because they were launched recently and they're still getting up to their higher altitude orbit. So it's not going to be a forever thing, but on the other hand, the more of them we get, the more there's going to be of that too. So it's a whole thing. So here is a fun little movie. I didn't make this. This is Morbid Jaw made this. And this is a simulation of all of the satellites that currently exist, as of July 2nd this year, as viewed from Rubin Observatory. So you may have seen a whole bunch of things flying around at the beginnings, like an all sky view from like 3 different projections. And then, you get close to midnight and things calm down a bit. There's not as many satellites in the way. I could probably find some patches of sky to put my telescope at. Life's not too bad. And then as the night progresses and sunrise gets closer, here come the satellites. So this is a potentially really big problem for observations that need to be done in twilight, which is a lot of solar system science, looking for killer asteroids. Lots of things that really can only be done at certain times of night. You can't just put off everything till midnight, as an example. On the right is the simulations that a colleague of mine at University of Washington has done for how many satellites will be visible at any given time. Spoiler, several. So the blue and orange lines on this plot on the right are for 12,000 Starlinks at like roughly where they'll probably be. So the bottom one is at midnight. You get like a few satellites appear at midnight, and then like the rest of the night or the rest of the year, you're fine. And then the twilight is where it's a problem. There's a constant level of satellites always at twilight. And then the green and the red are worse because instead of simulating 12,000 satellites, they simulated 48,000 satellites, which is the approximate number that Starlink hopes to ultimately have. And this is just Starlink. This is not any other satellite operator. So that's great. So SpaceX actually, I've been being a little snarky about SpaceX, so this is, an evening chat, but they've actually done a lot of really good stuff to mitigate the brightness of their satellites. And they've been collaborating with some astronomers, not directly with myself, but with some of my colleagues to take a look at how bright things are and how they can make it better. So one way they do that is during the orbit raise phase of before it gets to its main orbit. So like the phase that all the ones that you're seeing in the comet are in now, they are rolling the entire satellite body so that the sun reflects more off the edgy part than it does off the shiny part. And that makes it dimmer, which is great. So thanks. When it gets to the on station or operational normal orbit, then there's a couple of different things they've tried. One thing they tried is called DarkSat, which just sounds like, I don't know, some kind of villain or something, but it's actually good because they painted some of the surfaces, like literally they painted it black. It's like they write like, we coated the surface with a specular black paint. I'm like, you painted it black. But it kind of worked. And I'll show you how it kind of worked in a couple slides. The next thing that they're doing is called VisorSat, which I don't know what that sounds like. It's just a name. And this, instead of paint, they're literally putting a little visor down to block the light from getting to some of the most reflective parts of the spacecraft. So actually, all of the Starlinks from here on out are going to be VisorSats. All of the ones that were launched just like a week or whatever ago are VisorSats. The thing is that we haven't actually had a chance to observe them yet because all the telescopes are shut down because there's kind of a pandemic happening. So we don't have good observations yet of the experimental VisorSat that was launched in the previous set, and the ones that were just launched aren't at their final orbit yet. So stay tuned. We hope that this makes them significantly dimmer, and SpaceX thinks it will, but it's really hard to simulate satellites because, as we like to say in physics, they're not spherical cows. So, okay, a little bit of thing that I did I don't have the paper citation on here. Well, oh well, it's Tyson et al. 2020, and I can put a link in the chat later. Normally we don't intentionally observe satellites, but we want to be able to quantify the effect they're having on current and future detectors. So this is a little thing that I helped do where we took a picture of the sky when we knew there was going to be satellites. And then I took a look at a couple of the segments of the stripe of the satellite. Well, okay. I'm sorry. We have a toddler moment. As I was saying, the satellites do go across several of the camera chips, but I only actually analyzed one for each, just for simplicity's sake. What you can see when you do this is that there is a peak across the trail. So it's brightest in the middle, and then it kind of fades off on the edges. This is the left plot I'm describing. And then also the flux along the trail has these little bumps in it. Those are actually background objects. So if that was a star that you were hoping to study, you were out of luck. What I also found really interesting is that the satellite trail actually appears wider in your image if you have a bigger telescope, because optics is really cool. Normally, as an astronomer, everything that I look at, I assume it's just like a dot, or what we say is a point source, like super far away, but satellites are actually pretty close. So they have like a finite size, and they can see the size of the telescope mirror like from their position. And that gives the trail that winds up in your image a width as well. But this is actually good. So a bigger mirror gives you a wider trail. You might be like, that's bad. That's a bigger stripe I have to deal with. But it's an overall dimmer stripe because the brightness is spread out over more pixels. So it's complicated, but that's actually kind of good for bigger telescopes. All right, so what did I find? I found that this DarkSat thingy is 1 magnitude darker than its brighter siblings. Now, astronomers are weird. We use magnitudes. It doesn't make any sense. It's 3 times darker, okay? Which is good, but not good enough. We would like it to be 7th or 8th magnitude, which is dimmer still, but it's not. Hopefully, VisorSat will be. I also only did the observation in 1 filter. There's also different colors that Rubin Observatory will use. And I just did it in 1 of the 6 different filters. So, it's brighter in redder filters, so that's exciting too. So what does this mean for Rubin Observatory? Well, for one thing, I have a cool movie. So this is showing what happens when you shine a bright light at a CCD camera chip and see what happens. I did not do this. Some colleagues of mine with an actual laboratory did this. And what you get is these weird little overtone, they're called crosstalk, these additional stripes in the image. And as you can imagine, you probably don't want that. So they've been working on an algorithm to correct that. I'm gonna stop this from playing 800 times so we don't all lose our minds. Then in addition, some colleagues of mine have been working on a technique where when you stack up a whole bunch of images, you can mask and ignore the images that will go into that stack that have a trail, which is also a technique that astrophotographers could use in principle. And so you may be able to see there is a really faint, there's a movie in the way. There's a really faint little thing in the top right corner that is there in the left and gone in the right. And that is a successful use of the get rid of my satellite trail technique that we've been trying. There's other nasty stuff in this image, so don't look too hard at it. The data that we get from Rubin Observatory is going to be amazing and great. There's going to be stuff coming, like 10 million alerts of interesting changing things every single night. Hopefully not all of them are going to be satellites. There's also going to be these deeply stacked images, so you can do all kinds of different science. You can look at all these faint galaxies. You can look at how the universe's statistical properties are distributed, like at a large scale. You can look for optical signatures from colliding black holes. There's lots and lots and lots of cool science you can do. If you've heard of something in astronomy, chances are you can do it with data that we're going to produce. Of course, it's not going to start until about 2023, so that gives satellite operators 3 more years to put more satellites up. Woo! How will science be affected? So this is kind of the question that people have been working on a lot in astronomy. And the short answer is that no one is really funding us to study this in detail, so we don't have an incredibly clear answer at this point. And also, this is such a new problem. SpaceX was surprised that these satellites were as bright as they were. Astronomers were surprised that they were both as numerous and as bright as they were. This is something that just happened really quickly compared to the time scale on which astronomy usually operates. So we're all kind of still getting our bearings here. And we also don't know exactly how many satellites there will ultimately be or how bright they're all going to ultimately be. We only have a small subset of what's currently here. We don't have a future prediction. So Reuben Observatory is important because it has a huge field of view and a really big mirror. That means that it's really susceptible to seeing a whole bunch of these. But it kind of remains to be seen exactly what the impacts on a whole bunch of different telescopes around the world will be. That being said, I can give you a few interesting examples. So I mentioned earlier that twilight observations are important for certain science things. So we might not be able to find potential killer asteroids as easily if we can't take as many observations in twilight. Like, that's the reality. Time domain science, like interesting things changing just from night to night or hour to hour. We might not be able to see as many supernovae or colliding black holes. Static sky science, that just means like when you add up stuff and see the really faint, subtle differences in different parts of the sky. What you're looking for there is like statistical noise fluctuations in the background level. And it's a very precise thing you have to do. And if your background is actually a bunch of like subtracted little stripes every which way, people get sad real quick. There's also the potential for a whole bunch of unexpected discoveries from Rubin Observatory. It's one of the things I'm most excited about working on the project and helping do software. And we don't know how satellites are going to affect that because we don't know what we're going to find. Kind of the same things that make Rubin Observatory such a good discovery engine for unknown things is the same properties that make it uniquely vulnerable to satellites, unfortunately. So we won't ever really know if we have lost something there. Now, the good news is that we may be able to mitigate some of these by also running the survey for longer than the nominal 10 years, right? If you just keep taking pictures, and but you have to throw out the satellite ones, it's, you pretend like it's a cloudy night because we're used to those, right? So if you just do it for longer, then maybe it'll be fine. It'll be better, but you can't get everything back. And as I said before, funding is a little bit unclear, and it does take a lot of time to actually plan and build an observatory. So there are lots of, Rubin is like the first and biggest one coming up, but there are other observatories that have been planned and funded and are being built that are going to also be affected by satellites that we haven't even really begun to realize yet. Okay, so this is the part where I put on my personal little hat that is not sponsored by anybody and just share with you a few recommendations that I have given everything that I've shared so far. So the first and foremost, at least in my mind, is we should have fewer satellites. Like, I know that it's important to be able to do the broadband internet or whatever else that the satellite operators are trying to do, but I would really hope that they would put a lot of time and energy into trying to figure out if they can accomplish their mission with simply fewer satellites. The next thing I would recommend would be to try to keep them as dark as possible. I went ahead and put this like 44 watts per steradian number in here, just in case there's any satellite operators watching this talk. I don't know. I don't think in watts per steradian, but apparently they do. And interestingly, though, the 7th to 8th magnitude threshold for the darkness that we would like satellites to be at is just about the same as the threshold for what you can see with your unaided eye. So if you're hoping to go to a dark site and witness the glory of the Milky Way, then if the satellites are all 8th magnitude, they're not going to bother you. You're not really going to be able to see them. If you take a photograph, that's a whole different situation because you have a longer exposure, and that's a whole separate talk. I'm not an astrophotographer, but that's a fainter threshold, unfortunately. Lower orbits. This is a little bit counterintuitive because you think that if you could just put them high and far away that we would be happy and not see them, but that's not how it works. The higher they are, the longer you see them. And if it's going to be a zillion of them, you want them low so they're not there for long. They're also less in focus when they're lower. So again, that stripe in the image gets wider and its overall peak brightness is lower, which helps. We would really love all satellite operators to share high accuracy satellite orbit data so we know when and where to maybe not look if we have that option. I also think it's really important to invite people who are not just astronomers and satellite operators to be a part of this conversation, which is not something that I've seen happening very much because the night sky belongs to everyone. And most of the people who are being involved in these important early times of deciding, who's launching satellites and how many are there going to be and what should we try to do to make them less bright in the sky are just scientists and satellite operators. So I would hope that we could make that a little broader. Funding would be great. And I would rather that funding doesn't take away from science. Probably at some point, we will need to talk seriously about making the kind of mitigations that SpaceX is doing non-voluntary. SpaceX's mission is somewhat well aligned with astronomers' mission, and they both are like explore the cosmos in a larger sense. And so SpaceX, folks from SpaceX have said things like, we want to not impede astronomy. Like, it's important to us that we don't mess up your science. They've said that. You know, you can find the quotes yourselves. But not every operator is going to have that same feeling. And even when they do have that good feeling, there's still issues to address. To read more about this, please stay tuned for a white paper that's coming out really soon. I think in the definitely the next month, from a conference that I attended called SatCon 1, because we have to have fancy names for things like this. But it will be a publicly available white paper, a little bit technical, but I'm sure it'll be summarized in the news, and it will have a lot more detail about recommendations that are not just me talking, but that are like the astronomical community putting forth some recommendations. So this is me, and that will be the community, just to be clear. Okay, so this is my last slide. I put a lot of words on it because it kind of summarizes everything that I've talked about so far. So just to briefly remind what we've covered, with tens of thousands of satellites, the real situation is that no matter what we do, there's going to be some impact on science. Exactly what that is, it's a little hard to say because this has come up so quickly and they've been so numerous and also a lot brighter than anybody expected. The impacts of these satellites are really far-reaching. I mean, I care about astronomy a lot, but I also kind of care about living on planet Earth and being able to occasionally see the stars, despite being in Seattle where it's cloudy and light polluted. And the ecosystem things that I mentioned earlier as well. And also cultural losses. Lots of different religion and culture uses the night sky for a whole wide swath of things. This is not just science. In the astronomy world, wide-field ground-based telescopes like Rubin Observatory will be most affected. And I am grateful that SpaceX is setting a pretty good example by taking satellite brightness mitigation seriously. We're hopeful that the worst effects for Rubin Observatory in particular can be mitigated at this 7th to 8th magnitude brightness level, but fainter would be great. I should make a little theme song. And finally, it's unclear who's going to fund people to actually do this work. And at the moment, the mitigations by satellite operators are voluntary and not legally required. Thank you so much.
All right. I'm going to clap, and I'm going to pretend that I'm clapping for everybody here, but feel free to use your emojis to cheer on Meredith. Thank you so much for that talk. We have plenty of time for questions if you'd like to put those into the Zoom chat. I don't see anything yet, but maybe from our YouTube channel, do we have any questions maybe on that side of things, Jim?
Yeah, the first question that I saw that was a good question was, do we know if these mitigation strategies like the DarkSat, are these causing problems for the satellites? Are these going to make them overheat or anything like that?
So that was, I think that is one main reason that they actually have chosen to do the visor instead of the DarkSat, is because I heard like secondhand that the painting at Bellac did indeed make it a little hotter, and that did have some potential issues with operations. And I think that the VisorSat doesn't have that problem as much, but do not quote me on that. I have not personally studied it.
There's one other one sort of, I guess, kind of related is Sam L asks, what are the impacts of these numerous CubeSats? So instead of the Starlink sats you feature, but all these CubeSats, these tiny economical satellites, they're becoming more popular. What's the impact of those?
Sure, I've heard of those, and they're very small, right? They're like a meter or something, 3 feet across, whereas the Starlinks are bigger than that. They're like 3 to 4 times bigger. So I have not heard anything about people complaining about CubeSats in their data. I suspect that's because they are not sufficiently bright to cause issues and or not sufficiently numerous to cause issues, but I'm not entirely sure. They, do you know, Jim, do you know if they're like in a lower orbit also?
I think they usually are, because they get dropped off early, so they're usually pretty low.
That's what
so yeah, that makes them super low and out of focus too.
Yeah, so they're super low out of focus and not on top of, and moving pretty quick to be at that low orbit, then that might be less of an issue. Good question.
I've got a question from our Zoom audience. Rob Wickham asks, Why is twilight important to killer asteroid determination? And is it because they reflect more than other times of the day?
Oh, so yeah, they have lasers on them. No, I'm just kidding. There's no lasers involved. The main reason is that they are in the plane of our solar system. So the sun, and so when you look at the sky, the sun and the moon and all the planets kind of all line up along the same plane. And the direction that you're going to see asteroids in our solar system, they tend to be easier to find when you can point kind of close to the sun, relatively speaking, versus like randomly away from it where there's probably not going to be any. Now, in the off chance, there could be one at like some really weird orbit, like coming at you, but most of the asteroid populations that we would keep an eye on are more just going to be only visible closer to sunrise and sunset.
Cool. I have another question from Mackenzie Reed. Are there any concerns for ground-based astronomy in the far infrared band, say 2.5 microns to 25 microns?
Just give or take. Yeah, so the infrared is important for a lot of science, and we don't yet have a lot of observations that actually measuring the satellites in that band. There was, I think that, again, in the upcoming SatCon white paper, I'm pretty sure there is like at least a mention of that, because I know that one person got some IR ground-based observations that had Starlinks in them. And the main conclusion that I recall from that is that they are significantly brighter in the infrared, which makes sense, right? They're warm, they're got like battery, they have a solar panel, there's electronics happening. So they are brighter in the redder and infrared bands, unfortunately, than the GS middle of the visual.
Do we have another one from YouTube?
Yeah, we do. And it's kind of a related like mitigation question here from Randall Williams. Are there certain observatories like at different latitudes on the Earth that might be better positioned? Is there better locations for observing that would be easier without the satellites?
Oh, that's an interesting question. I guess you could always just do everything from the South Pole. They already have telescopes down there. So I'm thinking that for the most part, at least Starlink, right? They're trying to offer internet to everyone, and there's not a lot of everyone at the South Pole. So if you can get to a latitude that's like unpopulated, they might not have as many satellites there. But then you get into other issues, though. That's actually really interesting. I hadn't thought about that. Yeah, but there's no magical like, oh, if you go to the southern hemisphere, they're gone. Like, no, I wish. Yeah, you can't just pick a hemisphere and solve your problems, unfortunately.
And another question from YouTube from Jennifer Grasso, wondering, kind of going back to one of your early slides, how long after the satellite is decommissioned does it take to come back to Earth, the deorbit phase? How long does that last?
I don't think they've deorbited any yet, so I don't know offhand. Or maybe they've deorbited like 2 or something. I get it. It's like of ordered days. It's not like years. It's like days to weeks. Yeah, and I don't know how bright that is either. But it could be during day potentially. I don't know, maybe.
We have another question from Zoom. Casey Doran asks, are there particular tooling improvements that eager open source software contributors can make to help with these image processing issues?
We always love random open source software contributions in a general sense. So one thing that I have heard talked about but have not yet seen realized, and maybe people are working on this and I just don't know about it, but is an app of some sort that would actually tell you what satellites are overhead, like at any given time and location. Because there are several databases of these satellites that are publicly available. Heavens Above is one. There's a couple others that SpaceX actually push their data straight into that are queryable if you know how to query properly. And what I think one of the things that we really need for planning like individual one-off observations is a tool, but be it web-based or phone-based or whatever, where you can give it a location and a time and you can say, should I point at this nebula or should I wait 20 minutes? That would be really useful. Kind of analogous to what observers use today for like an air mass table. So when you're going to make your observing plans for like a smaller telescope and you have like a number of targets you want to look at, you always go and you look at like, okay, what time of night should I point at these things to figure out like where I'm not looking through too much of the Earth's atmosphere, or like at the moon. So you can do a similar kind of thing for adding satellite information in. And I think we probably need those tools. Now for Rubin though, Rubin Observatory is a different kind of telescope. It doesn't, you can't like put in a request to point at something with Rubin. It's surveying the whole night sky. And we have a little flexibility in how we schedule that, but we can't just avoid certain things at certain times quite as easily.
Great. We've got sort of a long question from David Westman. What is the impact of these satellites on radio astronomy? A Starlink satellite broadcasts a fairly strong radio signal from a direction that one normally sees natural objects. Since a radio telescope is a really large sensitive electrical thermometer, would the impact, or perhaps the impact would be severe?
So the first thing I'll say is I'm not a radio astronomer. And the second thing I'll say is yes, this is also significant in the radio. This is going to be the topic of an upcoming workshop in October that the IAU, the International Astronomical Union, is putting on along with some other folks. It's going to be virtual because everything's virtual. It's called like Dark and Quiet Skies or something. So this is definitely something folks are thinking about, but it's like I said, for the optical situation, it's like we're just starting to actually quantify it. The one thing that's kind of good in the radio regime is that there's already a legal framework for handling like radio interference and noise. You have to, purchase chunks of spectrum, and the cell phone companies are like trying to compete for like the really important scientific bandwidths, and it's like a whole thing. That little fun side reading project you can go look up if you're interested. But what that kind of regulatory situation does not exist at all for optical wavelengths, only for radio. So while it's certainly a problem, there's at least a fighting chance of mitigating it from the get-go.
Nicole, I've got a good question from the YouTube channel, which I think Meredith can answer really well. What is the impact on Hubble and other telescopes like this in space? Are any of them impacted?
So Hubble is actually interesting. Hubble is about, I think it's actually also about 500 kilometers altitude of orbit. If someone is, yeah, okay, Jim's nodding vaguely. I must not be totally lying. So it's also in low Earth orbit. And interestingly, there are some satellites that go higher than Hubble, and sometimes Hubble gets photobombed by higher orbit satellites. It's not very often, but I saw a picture and I was just like, oh my gosh, you can't even get away from this in orbit. But a little more practically speaking, sometimes people will suggest, why don't we just do all our astronomy from space? Like, if there's a bunch of satellites in the way, like you could just put your telescope in space and then that problem would go away. Sometimes this is asked in jest, and sometimes it's asked seriously, and lots of different ways in between. And the situation is that a lot of the telescopes that we build on the ground are really uniquely suited for the ground. Now, would it be amazing if we had like no atmosphere from a purely taking amazing pictures perspective? Sure. I wouldn't really want to live here in that situation though, because, the whole radiation air breathing thing, will be slightly problematic. And that's why we tried to, when we do build telescopes on Earth, we build them at really dry and really high sites so that we don't have to deal with quite as much of the Earth's atmosphere. Rubin Observatory in particular, right, it's an 8.4 meter diameter mirror, whereas Hubble is only like a 2 meter mirror. And I don't know how you would propose launching an 8 meter thing into space. James Webb Space Telescope is going to be like, what, 2 or 3 meters, something like that? I don't remember offhand.
No, it's like 8, but it folds.
Oh, it's like 8, but it folds. Okay, well, space origami. Just make everything James Webb. Well, that would be great. Would you like to pay for it?
I'm out of questions on Zoom. If you have any more from YouTube, Jim.
The last one, I think actually Meredith might be able to answer as well. From George Schaefer, wondering how accurate folks need to be if they want to make predictions for satellite trails and images, or make contributions to software. How accurate do you need to be? How well are these positions known?
Sure. It depends on how frequently telemetry is shared. But roughly speaking, these things move about 0.5 degree per second in the sky. So they're zipping along. So if you want to take a quick snapshot of something, you need to be pretty precise because you're either getting a streak in your host or you missed it. But if you're taking only a couple second exposure, you can just take another one, right? So there's some trade-offs there.
And the last question I had here was from Stephen James Burks asking, do we think the ultimate solution is going to be legislation?
I think that has an important role to play. I mentioned before that the timescale of satellites getting launched is like a blink of an eye. The timescale of like astronomy getting funded and happening is slow. Well, legislation's over here, my friends. So we're not quite there yet, and I do hope there is a path forward that enables the night sky to be shared, because I get that there's a lot of cool things that you can do if you have a bunch of satellites in space, but I also really hope that we can pass the dark sky along to our next generation.
All right, I think that's a wonderful place to end the night since we don't have any more questions. Thank you again, Meredith, for your fantastic talk. And for those of you who are still around, we will be starting our Instagram interview at about 9 p.m. I just put the AOT Seattle channel or Instagram account on the chat if you'd like to join us there. Thank you again. I'm gonna clap by proxy for everybody, and we'll see you at the next Astronomy at Home. Have a wonderful night, everyone.
Thank you.